Let's say if AWS gave you $5 billion to be exclusive on their platform, would you be interested?
I think a few people I really respect were quite technical, like Bill Gates or Mark Zuckerberg. They don't necessarily had fancy degrees, but they just see the opportunity drop out and went for an opportunity. I think like one of the success of NVIDIA is actually in their engineering structure. There is way less bureaucracy in between the layers, and it means they're still operating closer to the startups. So for the company at that scale, the way they organize, it's very impressive to me. I use GPT-2 myself using Python interface, and I've seen how cool those models long time ago. So essentially, whatever systems were built using AI under the hood has to have that interface that's very easy for people to manipulate. What is also challenging here is that when we talk about power limitation and dark silicon, if you actually make everything to run, you might actually overheat this thing because it won't be able to dissipate the heat as well. But that's where there are a lot of opportunities there, untapped potential that we at CentML in our company actually use for the benefit of our user. CentML is the company that focuses on optimizing machine learning workloads, both training and inference. Our focus is to make things easy to use, cheap and efficient for you.
You cited, Zuck and Bill Gates. You could argue that they've become less technical over time. And is that because they are communicating with stakeholders?
Wow, great question. So CentML is the company that focuses on optimizing machine learning workloads, both training and inference. Our focus is to make things easy to use, cheap and efficient for you when you try to build a new model, fine-tune existing foundational models, or deploy the models of your choice at scale.
Do you struggle being, I don't know how to say this, but you're by far the most technical CEO I've ever seen in my life. Is that something that, do you struggle with that? Because you're the guy who's normally, down in the details, you want to know how everything works. And now you're kind of like trying to coordinate everyone together.
So far, so good. I actually think that mostly give me an advantage, if anything, right? It's like I can save time of my CTO in many meetings because if they just need to understand what we're doing in general, I can handle most of these questions, right? So they can focus on actually building things. I think I partially as a life of a professor, you need to learn some of the business aspects of fundraising and built-in teams and all of that. I've been to industry, so I think it helps me to sit kind of in both camps, right? And I do like that in conversation with both customers and investors, I can handle the technicality usually as much as they can go, right? So I can handle pretty much any technical question. So I like it, but I can also cover everything business related. So I like they had a good enough understanding. I'm not a replacement for the tech team, but I understand what's doable, what's not. I had a good grasp of what our team can build.
In an ideal world, if it were possible, do you think every tech CEO should be as technical as you?
That's too much to ask, but I think a few other people I really respect were quite technical, right? Look at Bill Gates or Mark Zuckerberg and quite a few others that were successful were actually quite technical. They don't necessarily had fancy degrees, but they just see the opportunity drop out and went for an opportunity, right? But I think they're very technical and they do understand that space. And I actually think it's very important for the success of the company in this space to be technical. Look at Apple, CEO, at the beginning, it was all very technical, right? Really. And they do understand the space and the customers more or less equally, right? So it is important. It's not mandatory, like you can do the same with a very strong CTO or VP of engineering, but it's a good feature to have if you can have it.
What are the forces that erode that over time? Because you cited, Zuck and Bill Gates. You could argue that they've become less technical over time. And is that because they are communicating with stakeholders that have a different kind of horizon of understanding? Is that a pernicious, inevitable thing? Or do you think you can kind of hold on to that very high resolution view on things?
It's almost inevitable. I see it with me as well. So the minute you start to write code daily, you start to get a little bit disconnected with what's possible, what not. Not to the level you're completely lost, but it's never the same as what the engineers have, right? But like you can have both zoom in and zoom out at the same time, right? Like you need to have some, trade-off. So I think it's inevitable. Even in my academic career, at some point I had to admit I can't look at every line of code that my students are doing, right? I can't code with them. So I need to trust what they do. It's the same as with any management role in general. So I think it's a normal path, and the bigger the company grows, the more and more it is. I believe when I was young, we were like learning about how Bill Gates, for example, managed the engineering teams. And at the beginning, their testing was literally he was looking over every single line of code that goes into the product. Obviously, that doesn't scale, right? So you need to know how to trust others, how to build the team that scales and still successful and delivers things. But you being able to understand in a reasonable scale what they're doing is still very valuable.
Do you see that kind of organization building as an engineering problem?
Oh, very good question. I actually think, yes, it is. It's a very interesting problem in general. And I had a lot of thoughts about it. Usually right now, they're not my main focus because I had other problems to solve. But like I really admire, for example, what Jensen did at NVIDIA. Look, he's managing one of the flattest structures, engineering-wise and in general in the company. And when I met with him and like asked about how do you manage this, he's like, oh, I had in like 50 direct reports or something like that, right? It's it's a very different scale. It's very hard to manage 10 people. Like 15 people is more or less the limit, right? And he manages that many. So it's a very interesting scaling problem. You definitely cannot do like one-on-one meetings. You need to figure out how to meet with the teams instead. But people are doing that and they're very successful. And I think like one of the success of NVIDIA is actually in their engineering structure, like in general company structure. They actually very flat, right? And it means that a lot of people know what others are doing. There is way less bureaucracy in between the layers. And it means they're still operating closer to the startups than a lot of other big companies. So for the company at that scale, the way they organize, it's very impressive to me. So yes, I would actually love, not necessarily have 50 direct reports, but I do want to have more flat structure. It's very important to be efficient. I see how extra layers easily can make things complicated.
Are you, I don't know whether it's fair to say this, but if NVIDIA has that kind of structure, it's a bit more centralized. And we'll talk about this a bit more later, but do you think that there's something good about having centralization?
There are definitely good things. That's a very old debate about being fully free and decentralized, right? Like some companies, I don't know, say Google comes to mind as an example of a more decentralized structure on something more centralized. I think centralized is very efficient where you're on a mission to deliver something. Like usually startups are more or less centralized, right? You had a very limited amount of resources, vision, and the main advantage versus others is the speed, right? You can go much faster, much more efficient than others. So this is why the decision has to make the right way, and you don't have the chances for mistakes, right? So in a way, for some critical features, that's really a requirement, right? But again, long term is just very hard to maintain it, right? I don't think others didn't want it. It's just very hard to live at that pace. And of kudos to Jensen to be able to keep doing this over so many years, right? It's really taken a toll on you, I'm pretty sure. Yeah.
Cool. Well, in which case, we should slowly kick off the interview. So I want to introduce the audience to Gennady. As I was just saying, probably the most technical CEO I've ever spoken to. I think it's remarkable, actually, especially when you look at the research that he's done. But Gennady is the co-founder and CEO of CentML, an associate professor at the University of Toronto. I love that university. I was there recently interviewing a couple of guys. And you're a faculty member at the Vector Institute, a research co-chair at ML Commons, a founding member of MLPerf, and you've also been a researcher at Microsoft. You've got a PhD from Carnegie Mellon University. You've had internships at NVIDIA, at Microsoft Research, and you're at IBM. And I mean, basically, you've done a lot of stuff, which is really cool. Welcome to MLST. Thank you so much for coming.
Yeah, well, thanks a lot for inviting me. Really excited to be here and to talk with you.
Very cool. Okay, so why don't we let's start with the low-hanging fruit. How do you think open source models compare to proprietary ones?
Well, it's a very good question, and definitely there are a lot of different opinions here. What I can say from my experience and my perspective is open source models are really improving over time. Like they're really getting closer and closer. There are a lot of different benchmarks. To the extent we can benchmark things and assess things, they are closing the gap over time, right? And I actually think it's good for the society and the IT space in general. It's nice that the models are accessible to a wider community of developers and people in general, that they can use it and build on top of that, right? Why this happens, I think it's fundamentally when it was clear that AI is so important to the world and the value it generates are all in front of us. There are a lot of people that got interested. And obviously, well, so many people got interested, they start to be creative and add value. It's very hard to be just this one company that is go ahead of everyone and release it to the rest of the world, and the rest of the world learns from you and doesn't catch up. Like no matter how smart are you people, the rest of the world is so much larger. And people have seen this through many other software products. Like the minute you make it available to the world, it is really important, the world will catch up quickly to you. And I think that's what happened right now. Yes, there are a lot of great proprietary models right now, but models like open source model like Llama and Mistral are also very high quality.
I mean, what kind of advances do you see in this space? I mean, I've been reading about, there was that paper talking about RNNs are coming back. There was that Min-LSTM and so on, and we've had Mamba and state space models. I mean, what do you think we're going to see any big shifts in this space?
The shifts are always possible, but I had multiple conversations with many prominent people in the AI space and the pure AI field. I don't see any obvious replacement for like attention-based blocks that use transformers, right? So I think a lot of focus right now is actually in building on top of that architecture, right? And there's always a chicken and egg problem. This basic concept ended up being really well capturing the different properties of the data we're dealing with. If it's good enough, and if hardware and the software evolves around it, it becomes like almost like a dependency that it will sustain being around and like it's not going to easily disappear. There are several different types of models that people suggest in built-in startups, but I didn't see any of them as a clear replacement. Whenever they really need to compete in the benchmark, they really usually use some form of attention mechanism anyway, right? And there is still plenty of room to improve around attention and transformer-based models, so I'm not particularly worried about that we're stagnating or anything. I'm more excited about what people are going to build on top of it, because I was at this event last week called Intelligent Applications, where we actually, as a company, won one of the Rising Stars Awards, and it was very clear people excited and see beyond the models. There were several fireside chat there saying like it's not just models, it's about building those sophisticated systems on top of the models that had multiple different components. That is very critical. So it's like core foundational models are still there. They're not going to disappear. They're important. But people are looking, what do we do next on top of it? So let's say 1 year ago, it was fine-tuning. People were excited about it. Then it was RAG. Now people talk a lot about agents and compound systems, like Databricks talk about it. This is very exciting things, and I expect that will keep moving. So people build not just a model, the new model. People build applications, something that the world can use right around it. And I think that's what's even more exciting than building a pure new model right now.
Yeah, Francois Chollet's term is this progressive disclosure of complexity, and I love that. But of course, you're a guy that's at the bare metal. So you're building compilers, you're building kernels, you're working with the hardware. You know exactly how the hardware works at the very, very lowest level. But you're still talking to this sandwich that we're building. So we're going to have abstractions on top of abstractions on top of abstractions to build these systems.
Yeah. You're absolutely correct. We had, and my team and I personally had a lot of background in computer architecture systems and building many different layers of the software stack. But I think this is our expert. That's what we're good at. But what the world consumes is the actual applications, right? I think that's ultimately where the value is coming from. People were excited about the models, right, and some pieces because that layer never existed before. Out of a sudden, we get another knob to play with. And obviously, there was a lot of excitement. We spent several years building those models. But then we reached the situation where we say, okay, it seems like to find something that scales well. So let's kind of start to build on top of it, right? And I actually think whatever we're building, that sandwich, how you call it, would be valuable no matter what the model is. Like tomorrow, someone would replace like attention with another model. I don't know, like space, like some of the space model that people discussing right now, like SSMs and others. Say this will become a new thing, but that would be just a block-in replacement, right? You would just replace one model in the sandwich with another block in the sandwich. Yes, it would change hardware utilization, but mostly that would be visible by us, hardware people, compiler people. The rest of the world don't even need to worry about it, right? They would just get a better high-quality responses, right? So it's very important to me that we don't stick to the model alone in terms of what we contribute, that we contribute to the rest of the stack. People still can evolve new model, build new things, but if the stack is mature enough that people generate value, this is much better, right? Because if we only all invest in building better and better foundational models, at the end of the day, there's no use case that people benefit from it, right? We're just going to burn a lot of resources and not having a really tangible outcome, right? So I'm not worried about the new model will come up. I think the system-wise, we're going to be much better, right? Ready than we were at the beginning.
How much coupling is there in the stack? We like to think that we're building these little decoupled atoms of computation, and we can just kind of build on top of it and build on top of it. But there must be some very complex behavior between what emerges and what properties the overall system has as a function of swapping out those components.
Well, that question has many different layers. At a very low level, our agents, like what's running under the hood are the kernels, right? And that's running on the actual hardware. So the entities there are the chips, and this chip communicated with some formal communication medium. So it can be either internal interconnect, like something like NVLink, right? Or it can be something that connects multiple nodes. So it can be Ethernet or like Mellanox cards, or something like proprietary optical interconnect that Google is using right now. At the end of the day, at that very level, those entities it's a hardware pieces, right? We program them in a certain way, and their interactions are very predictable, right? They behave in the way we program them to behave. There is certain level of complexity with them. There's not a lot of uncertainty though, but those are very repetitive. Like if you set up a training workload, an inference workload, like even though you run billions of examples, all the runs are more or less identical. There's a very little fluctuation. There are certain things like frequency that can fluctuate, but almost all the other things are fixed. So here, after we program the chip using either manual effort, or the compiler, things are predictable. But it's very exciting to think about what people can do with that hardware and the software stack. That is way less predictable. So the compound system, or the general systems built out of agents and other players and models, can be very unpredictable and very exciting. So this is a very open field. And I'm not going to pretend to be an expert there, but I think it's a very, very promising field where it's even hard to imagine where the limits are. With the hardware, we know that there is a certain limit on what we can achieve with that technology. After the chip is fully utilized, that you're at max, right? And even if you're at 80%, you cannot go jump way more far. But it's how the hardware is used, the sky is the limit. There's no limit. So we just need to make sure that people's creativity is not limited by the complexity of that stack. We just make sure that even kids can experiment with it. So essentially, I think many people said it was the beauty of ChatGPT, for example, for many people. They're never aware of the technology. I use GPT-2 myself using Python interface, and I've seen how cool those models long time ago, right? Not necessarily as good as GPT-3, but very powerful, right? But for the rest of the world, that was so mind-blowing because the interface was a command line, similar like in Google search, right? So essentially, whatever systems we built using AI under the hood has to have that interface that's very easy for people to manipulate. And it doesn't have to be just a Google search it's our voice. It's like us manipulating with the rest of the world, potential augmented reality. All of that can be really nice inputs, right? And this is where I think things becomes very open-ended and very unpredictable on what humans can build with it.
Just a quick point on the predictability, down at the hardware level. I interviewed someone from Cohere for AI at ICML, and they've got a paper out saying that there are differences when you run models on different hardware. I don't know whether you've seen that, and apparently the differences can be significant, especially on the long tail, for things like fairness. Have you seen anything like that?
So you mean that the results are different depending on which hardware you run it on? Yeah. So
Yeah,
I
there's the
think
same model on different hardware.
there are two things here that a lot of people don't realize. Let me clarify it. First of all, the way we run training right now, even on a GPU, forget about different hardware, just like canonical GPU, it's quite non-deterministic, right? There is a component there that would, if you run the experiments multiple times, it would ended up being different. What people don't understand and why that is fundamental to the way we manipulate with floating point numbers, right? So it's like every time you run, if you add up the same numbers in a different order, the result would round it up being different, and stochasticity of the neural networks would make it go one way or another way very easily because it's a very multi-dimensional problem. So it's like you're running the same experiment on the same hardware, it can go different. Between different hardware is even more differences because they could easily use very different precisions. So I don't think that, for example, we run experiments, my both research group and the company, we operate on NVIDIA GPUs, AMD GPUs, Google TPUs, Amazon Trainium chips. Fundamentally, you can get convergence on the models very similar in all these models, right? But you need to be careful with the precision and everything, right? So I don't think the hardware is guilty of anything. Hardware does what you build it for, right? And it usually has certain level of precision. But if you pick a chip hardware with low precision and not very careful about the convergence, you might have very different results. I don't think the hardware fundamentally changing the way the computation is done. Just computation is not fully deterministic, right? So because of that, you cannot expect a completely identical results. Like if you ask the same question to ChatGPT, it's not going to ever respond the same way, even if it uses the same chip.
Yeah, it's really interesting because, when we build normal computer applications using C++ or whatever, we say to ourselves, oh, we can verify it, we can test it, it's deterministic and so
Yeah.
on. And that may or may not be the case. But now we're building the next generation of applications. We're building AI applications and they have increasingly sophisticated behavior and we grow them. We don't design them, and we're starting to build agent-based systems and so on. I mean, how does that look to you?
It's a very interesting problem and challenge at the same time. Think about the very critical areas like automotive, for example. They prefer to have proofs for every little piece they build into the car. And now you give them a piece that says, oh, it might be non-deterministic, right? It might change this behavior. So it is challenging, and why it's like using AI in some of these areas very difficult, like self-driving, for example, right? So again, we need to find the way where we keep those errors within boundaries, or for example, we make sure that we use a precision that deterministic, or we limit some performance characteristic of the chip, but making sure the threads run on the same order. So everything is in the same order, and you use int8, like integer precision instead of floating point, and then things become out of sudden deterministic, right? You need to make certain changes, but you lose a lot of performance if that happens. So in some critical areas, that might be the outcome. In other cases, I think we just make theory around neural networks in general more robust so that we're more susceptible to noise. And there were several really great papers I've seen in the community where people try to stabilize the training process and the model and be less sensitive to noise. So that's in general. Like there are several problems that need to solve. So reliability of these results, reproducibility, and all of that is really, really critical.
Just coming back to the open source thing quickly before we move on. What do you think are the sort of like the implications for using these models like Llama and Mistral, etc.?
I do see a huge value for them, and not only because it's very valuable for me and a few other companies like mine that actually using them, and for I think it's very valuable for our customers. Why I see so? So a lot of their enterprises, I think they are critical for AI to actually generate significant value for the world. So again, when OpenAI or Google benefits and invest into a new big, nice, shiny toy like AI, they can burn billions of dollars and there's no outcome. I think for me, unless there is a benefit for this second wave of adopters, like Fortune 500 companies, for example, that's not really a success yet. Those companies always don't have as much expertise in AI, like as these companies I mentioned before as a first wave. So they probably, most of them, not going to just build their own foundational models. And they also had a lot of their own sensitive data. So if you combine those two things, you see that they either have a choice, either give the sensitive data to someone else, like another hyperscaler or a startup like an OpenAI, or you actually leverage the open source model and go the path that require way less expertise, like fine-tuning or RAG with their own data. This way, they would generate way more IP, right? And I think more and more companies right now go into that direction. So that's why having models like Llama and Mistral not only to exist, but also had performance on par with like models like GPT-4, right, is very critical because people can build their specialized models on top of it, right? And not dependent on any particular company invent this technology. They can build their own IP and they feel much better about because they control it. It's internal, right? So they don't feel like their business is fully dependent on that. They had to give customers data to something that's very less reliable. So that is making easier for the enterprises to adopt this technology. And it's very important because they would see all this risk before. It took them a long time to adopt like using cloud, and not all the data is still in the cloud, as you probably know, right? And again, the same would be with AI. Like people want to make sure that we can benefit from that technology ourselves and we can build an IP on top of it. So I think having open source model is super critical for that. So model like Llama, Mistral, and others, and Falcon are very, very critical for this trend to exist and actually the people to benefit from it.
But what do you think the performance gap is? I mean, it's quite interesting that OpenAI, they've shifted the narrative from we're building AGI systems that can reason and do anything. You know, on the new version, they've released a fine-tuning API. And they're kind of hinting that actually, if you give us a thousand examples of like some labeled imagery, it'll do better. And of course, it's the same for Llama, right? You can just fine tune it. You can just give it 1,000 examples of your thing. And I guess by increasing the specificity, you can make it for that application every bit, maybe even more reliable than GPT-4o would have been.
Yeah, so it's like obviously like everyone's gonna adjust to this reality and like OpenAI adjusting as well. It ultimately boils down to whether you are comfortable giving this data to them. It's like visual data points that might be sensitive data, not sensitive data. It depends on what the model is. If the people know that exists the open source solution that's reliable and verified by the community, that can actually be used instead, if the quality is comparable, then you would just probably go with it, right? Why take in for an extra risk, right? At least that would be my choice. It would be a different story if there would be a huge performance quality gap there. But I think this gap, as I said before, is shrinking every single time. Right now, it's even hard to say if there's like a significant gap between like some benchmarks. Llama 3 was as good or even better than GPT-4. Obviously, they also keep improving, but Llamas also keep building new model. What I see in the last couple of years that gap is always shrinking, right? I don't think this gap is growing. This gap between open source model is shrinking, right? And there is enough players here that could keep it exciting.
What's your take on O1 preview? And I don't know if you have any interesting intuition on how it's done, but people are talking about it being process supervision or something like that. And do you think something like that could be done on a model like Llama?
It's a very good question. I think it's definitely a step forward. It's a very nice model. Like I play a little bit with it as an amateur, as a user, right, without going deeper. It's interesting that for some things it's taken many, many seconds to think and give you a very basic answer that like GPT-4 would give you much better, right? Yeah, so I think that's quite funny. But and some other logical problems, it's very interesting, like on how it can do it, right? So again, to me, it's a step forward, but it's very hard to say how much of a gap it with the rest of the world is there.
Like there were these scaling laws, and you can introduce what those are, but they seem to suggest that there's almost no ceiling. We can just scale the data, we can scale the training, we can scale the model size, and now they're saying we can just scale the inference compute, and there's almost no limit to where it can go. I mean, what's your take on that?
Well, I think part of that is sad and done more for investors than for engineers and scientists. Will understand that all these exponential laws has limits, right? And you're gonna hit them relatively fast, usually. Uh, so I think reality is that training scalability laws start to diminish in a way right? We're limited by the amount of the data. People already start to use synthetic data. We don't have sometimes enough compute, and we understand that a lot of the benefits of adding extra data, if it's not high quality data, become very diminishing or even hurts, right? So it's like the big is not always bad. I think I've seen one recent benchmark, like literally today in the morning, where Llama 13 billion model, the older version, has a worse performance than Llama 1 billion model, right? So it means like the it's not just about the scale that matters, the quality of the data, cleaning, like how you train and post-training process matters a lot. Same for inference. I don't think it's an infinite scaling going on here, right? It's ultimately, yes, you can scale the model further, keep getting improve the latency, but the question, do you really need it? Like I've seen some of these benchmarks saying, I can speed up, the inference for Llama model by another like 50x. But when I look at the baseline, it's already at the human, it's like 10x faster than we can ever read, right? Like, what's the benefit of that, right? So it's very important to put things always into perspective. What's the benefit of that? For me, it's way more impressive if you not just improve the raw latency, right, on inference, but you could actually do it the most cost-efficient way. Because at the end of the day, that's a very, very important factor in the adoption of the models. So it's not a matter of like how far we can scale the inference and the models and how big a models we can still run. It's a matter of like whether those models actually do the job well and whether you can get that in a cost-efficient way, because that's what the customers want. And at the end of the day, they're not going to run the largest model available. They're going to run the best, the smallest, and the most efficient model that would do the job for them, right? And that's what's the most important one. And I think that's not covered as much because that doesn't sound as sexy as like talking about the biggest possible models. But at the end of the day, this is what the customer wants. Like they just want to make sure that they get the best quality for the minimum amount of money.
Yeah, I mean, I was watching Lex Friedman interview the Cursor team the other day, and it's really interesting hearing about how they designed a whole bunch of the models. So there's a tab model and there's an apply model, and naively using it, I thought, oh, they've just used like a big model and they're just kind of generating the entire code file. And for that reason, I thought, yeah, it'd be great if we have more TPS because I can just generate my code faster. But apparently, to make it work reliably, they've had to do all these ridiculous optimizations. They're using like speculative decoding, and they're like partitioning the code file up into all of these different tiles, and they're running it in parallel. And even in speculative decoding, you're like running it in parallel with a smaller model because they say code is lower entropy or whatever. So it's just an example that we have this notion in our mind that, oh yeah, we'll just have a big model and it will just do all of the things. But actually, a lot of the innovation is when you take a specific task and you just optimize the hell out of it.
Yeah, it's a lot of is really exactly what you said. It's because ultimately this is where the value is coming from. The value coming is not from randomly get one metric selected and benchmark it to death. Is actually working under multiple constraints. This is actually much harder because if you just had one metric, it's much easier to optimize and you say, oh, you need to be fast enough and highest and good throughput and the cheapest possible and low power and low emissions, and like all this constraint exists, right? And ultimately, when all these things go to scale, those constraints will be there, right? We already see like power limitations, compute limitations. People would have to obey those limits, right? So you actually need to build the system optimizations knowing that constraints are coming, right? And it's like in a lot of reality cases, it's not like, oh, what's the best I can do on the most expensive available chip? The customer would say, I have some compute on-prem, I would have some compute in the cloud, and I have all these different workloads given me by my data scientists and product teams. What's the best way for me to run them? Whatever is critical to run on-prem, whatever can run in the cloud is got overflow to the cloud, and whatever is free to go anywhere would go there. Like how you orchestrate all of that and how you deal with that's complexity you need to solve. And this go way beyond just optimizing a single model for single metric, right? And this is what we are building in the company. Like we are trying to get people the help of addressing multiple different complexity of metrics. This is what a typical enterprise or mature company would want, rather than like someone that just playing with one model.
So I interviewed Sabaro Kambahati, and he was like one of the biggest LLM skeptics. He had all of these papers out, testing self-verification and a chain of thought and so on. And he was using this blocks world problem, which is a planning problem. And he found that when you do mystery blocks world, so you change the tokens, it's the same problem, but you just randomly shuffle the tokens, or you put like random descriptions in the tokens. All of a sudden, the models don't work, because he was saying they're basically kind of, approximate information retrieval systems. But on O1, he seemed like a changed man. I was surprised. He was kind of saying, oh, look, they now have non-trivial performance. They're solving blocks world problems, sometimes many steps ahead. And I've tried it on some problems that are NP hard, and it's still, for a very small size of the problem, it still did something. So it's doing something. Like what is reasoning, and what is it actually doing?
I think it's a complicated problem in general. I think there definitely was one thing that was missing from a classical LLMs to me. Essentially, there was this problem of what you can memorize from the world. Like LLM is like a great filter that memorize a lot of things from the natural language. But to me, it never actually could reason in any complicated way. Like the good examples I've seen in some of the presentation was like it cannot do like 3-digit multiplication well. Like good luck doing it with LLM, right? It would memorize a lot of corner cases, but it cannot do the proper multi-step reasoning. And that was missing. And there were people that always try to build the AI around the reasoning aspect, but it felt like there were two separate camps that don't really talk too much to each other. But right now it starts to come together nicely. And I think that's probably a good step in the right direction here with this O1 model, right? There where, yes, it's for some very basic things, it's taking too long of thinking, but at the same time, it actually starts to look more human in a way that they actually start to do some basic reasoning, right? Which is good, right? It's not just memorizing things and just filter it, because even our brain, it's not everything is so sophisticated. All the parts of the brain, similar to like animals, we're just doing like object detection, right? And that has to be. You don't need any sophisticated reasoning there. Like you need to do it very fast or it won't survive, right? That's critical. And there's a part of the brain responsible for that. But there are other parts of the brain that develop much later in the evolution that actually can do basic math and things like that, right? So that one would take much more process. And we see like how we teach our kids. Like if you have small kids at home like I do, like you would realize that it's like they would learn object detection very early in their life and they're very good at it. And they don't need 1 billion examples. You just show them a couple of examples and they can get it, right? That's another, direction for improvement for those models. But like teaching them math takes many, many years, right? It requires way more examples such that it can solve any analytical problem. And it's very like long-term process. So I think it's the case here. We need to develop AI that would do this. I think in addition to this reasoning capabilities, what's missing to me in modern AI is connecting it to the rest of the world. I think that's what slowed down the training process right now. It doesn't have the context. It doesn't understand what the world is like. And because of that, it can do very basic mistakes, and all these hallucinations could have been avoided if the model would have ability to have a sensors in the world and collect the inputs and adjust accordingly, right? It doesn't have that experience, and because of that, a lot of things look like stupid or dumb, like still to this day. So I think that's another missing point. So like reasoning capabilities, definitely, but also ability to connect with the physical world that we as humans have. As we add more sensors and ability to sense the world in the process and having a notion of the world somehow as a part of the model and physics of it, it would help tremendously to improve those models' quality.
Yeah, I completely agree with you on the importance of embodiment. I think it comes down to the semantics gap. So clearly we have access to richer semantics because there's huge causal chain of things that happen outside of us, and that helps us understand and actually cognize. But the other thing is that there's a real problem with ambiguity that I see in these language models, which is that even with O1, sometimes it can get the right answer, but it's simply because it hasn't understood you, because you get better at prompting over time, of course, so you learn to kind of specify, the tiles can only move this way and they can only move between adjacents, and you kind of get better at it. But we have this remarkable ability to deal with ambiguity. It's a real hallmark of human cognition, and I'm not really seeing that yet, because I think when we do overcome this kind of semantics gap and ambiguity gap, I think potentially the models could be more autonomous. But the other thing I wanted to comment on is as well as this kind of semantics gap, I think that there might be a computational gap, and my co-host Keith Duggar is always at pains to point out that these things are not Turing machines. Like there's a kind of difference in kind with a Turing machine, which means there is a space of computation that they can't learn with stochastic gradient descent, much less perform. I mean, do you think there's some weight to that, or are you one of these people who just said, well, in practice it doesn't matter because we can just build systems which are Turing complete?
I think probably more on the second camp. I don't see the fundamental limits on what cannot be learned, right? I don't think we had a computer inside of our brains. We just had a very good adjustable system, right? And I don't think there is anything that we have cannot be mimicked to a reasonable extent. It's very complicated. It's going to take many years. I don't think we're going to have the AGI like next year, but I think it fundamentally can be learned, can be improved, right? And we can see on how we interact with the world, how we learn as humans, and a lot of that can improve the models we build as well. Plus, they have also their own capabilities that we don't have. Like, they can remember everything they've seen, right? They don't forget things as easily as we do, right? We had a great way to deal with complexity of the world. Well, we filter things greatly, but because of that, we'll lose some context. But, machines won't, right? So that's the advantage, right? It's like some precision. So there's pros and cons here. I think we fundamentally have the ability to compute everything we need. I don't think there is yes, maybe certain things with stochastic gradient descent are not perfect. We're going to do certain things that can be done better. For me, as a computer architect, I'm less concerned about what is computed, but how is it computed? I think we're ridiculously inefficient when I think about how much power our brain consumes versus how much power a training process consumes in modern data centers, right? That we're starting to talk about nuclear reactors back in US and things like there's not enough power and things like that. I mean, it kind of tells you, well, we go quite aggressive in one direction and we probably want to do some adjustment, right? So it means we need to learn how the things has to be done less aggressive on crunching numbers without thinking about what you're doing. You need to be more selective, and it has many different dimensions. It's the data, it's what exactly you compute. It's like not doing the same compute too many times. Like for example, right now, like every single foundational models keep starting with more or less similar data sets on everything they get from the internet, right? And that's quite redundant, I would say, like doing this again and again and again. So hopefully you can do that in a more iterative fashion. So the future models are not built from scratch, but actually built from a corpus of the prior knowledge, right? You're just additive to this, right? So I think that would be really, really important. Yeah.
Yeah, I've got so many things in my mind. Just to close the gap on what we were saying before, there's this ambiguity thing. And at the beginning of this interview, in a way, it's a bit nerve-wracking because it could go in any direction. And just like with a language model, when you have a long conversation with a language model, the mutual understanding increases because it's almost like the entropy goes down. You're on a well-trodden path. And it's a similar thing with our discussion now.
That model also train you, like you train the models, or they train us to ask the questions in the way they understand. Like, my kids very quickly realize if you don't ask questions ChatGPT in the right way, you don't get the high quality answer. But if you learn the protocol and how to communicate with this thing, you get what you want very quickly, right? So that's very impressive. Humans also adopt to the behavior of the machines.
Yeah, exactly. So it's all about knowing what question to ask.
Yeah.
And it's so common in software engineering. So because these cursor guys, they made the observation, I don't know whether this is true or not, but they said that code was lower entropy. And, I have noticed this to a certain extent. You put a load of code in there and straight away it kind of like snaps into some kind of understanding. But still, if you ask it something dumb, like if a level 7 engineer from Facebook went in there and they would know what they were building, that they would be using the right kind of abstractions, they would be kind of designing things correctly. It's a mistake to think that anyone can go in there and just write some software, because it just gives you back exactly what you ask for, and that's quite often the wrong thing.
Yeah, I don't think I think it's misconception when people said they would replace human but I think that is we're quite far in my opinion from that, right? It's still an assistant, a very high quality assistant. So you really need to, like, you're still a designer. You're the one know that's what's missing. But for example, you don't need to memorize this particular algorithm to do this, like, like the best sort or the best walk pass through or the best graph traversal, right? You just don't need to memorize it from a textbook, right? You just know roughly should it look like, and you know roughly the complexity, and then you just ask that question and it would give you the code. So instead of you figuring out how to write it and debug it, right, that somebody would give you those like very basic concept. And a lot of things when we manipulate data as a software engineers, we doing repetitive things again and again. And this thing learn from us doing this and what's the best way to do it. So you just need to know that you need to do this task, but you don't need be the best of doing this model anymore, because there were thousands of people that did it better than you, and it's already part of the corpus, and it's gonna give you. So you're gonna start building off to a very good, reliable pieces. But without the designer at the top, it's not gonna be able to be like. Good luck asking it to build a new operating system, right? Like, just good luck, right? That's just like it's not about or just adding a few for loops here and there. It's actually quite sophisticated piece of stuff. But yes, if you want to build a very basic, operation with a web page, right? You don't need to learn about that standard APIs. It's all will be there because it's very standard. So it will save you a lot of time of learning those things, right? Yeah. It obviously creates some danger if there's something wrong and fundamentally buggy come into its code base, it's going to now suggest it to everyone. It's going to be do everywhere, right? But like it's the problem with like any library. If the library has the same problem, like it's like everyone would be susceptible to it. So I still think about all these coding things as not being replacement, but being just very solid assistance in the very best case.
Yeah, there's this thing as well that right now coding is, Gen AI coding is still human parasitic. So one of the problems the Cursor guys were saying is the verification problem. So you're telling it to do something, you ask it the right question, and now we need innovative ways of just diffing many, many files, because it might have generated 400 lines of code, and the Git experience, like on GitHub, we've got this multi-file diff experience that hasn't changed in like 15 years. And now we might have layers of LLMs that are kind of helping us focus on the bits that change. So we're becoming verifiers. But still, though, what we don't want is a system that just tears up the code base every single time. John checks some changes in, and now there's changes across 50 files, and that creates this understanding debt, because now all of the other developers need to figure out what's going. So there is something to be said for having a very modular architecture which is understood by everyone, and then even though we might be introducing inefficiencies, we make changes in a targeted way because we want to minimize the damage, if that makes sense.
Yeah, absolutely correct. The design is like, it's not just an engineering, it's an art in a way. Like designing a complicated system that functions efficiently and scales is an art, right? Like it's like you need to do it. And I don't think we're at the stage where we can delegate that responsibility. So we delegate some more mundane work, to people. There are definitely some risks associated with it. We start to touch with you. Like I think I see it this way. But then for many, many years, we rely on the people going through the ranks in the software development, like software engineers, junior ones. They don't go into design of the whole system, right? They learn from the basic tasks. Right now, if we start to, some of that functionality would be replaced by assistants, right, of different sorts. We need to make sure we have a good basic learning curve for them. Like if we want to raise a new, generation of architects, like the people who build the system and raise from L3 all the way to L8, L7 or L8, right? We just want to make sure that have ability to grow, right? In the new environment where a lot of the basic skills are replaced by automatic tools. I think it's doable. We just need to find the way to do it. The whole process needs to change. I think even the interview process has to change. Right now we were testing people a lot on memorizing some basic concept. Right now, why would even need it, right? Like you need to test more of a design skills, like on how you use these components rather than memorizing the best algorithm to do it.
Yes, and also surveillance. I was saying to you last time we spoke that I'm a huge fan of the actor pattern, and you have to become an expert in surveillance. So all of the actors are logging their activities, and they all happen asynchronously in different, in a different order. And we need to build the next generation of platforms just to figure out what the hell our systems are doing. And but it's also more flexible, right? Because we can do simulations and counterfactual analysis and God knows what. But we are moving away from this old school of software engineering, and that's kind of what I wanted to talk to you about, because enterprise adoption, right? At the moment, the enterprise that they've been building software in a certain way for a very long time. Yeah. There have been ways to make it more accessible, like low code and no code platforms and so on. They're starting to adopt AI. What are you kind of seeing? What's the state of play with enterprises adopting AI?
Yeah, there are several things that we see as a company here, and again, that helps me to have a company behind me to had a little bit of experience here. They're definitely like majority of the companies we talk to, right, and the enterprise segment, they're on board with GenAI. They see the potential of the value for them. They very frequently have the budgets already allocated to start deploying the technology internally. Where things become complicated is what exactly that the first use case been. They also sometimes don't have the right conceptual understanding what's doable, what's not with that technology, right? Because usually the way it looks like someone in the company would say, okay, let's start to use GenAI. Internally, decision is made. Then they start to get some people from the internal organization, say data scientists, that would help to adopt the technology. This data scientists are excited about it, but they never actually built sophisticated system. And plus, this is a new tool. So there's all this complexity. We never built complicated systems ourselves before. We were scientists, right? More in the AI space. Out of sudden, we need to do it. And this whole thing itself is very complicated. And the system is very complicated built out of it. So it's very hard. And also you need to find that killer app within your org to justify your existence. So it's very easy to come say, oh, give me $5 million. I'll train another GPT for company X. And we had our own model and our own IP. That's great. But do you really build anything helpful for the company? That model probably going to be much worse than Llama, right, that you could have used, right? And then instead you should probably do fine-tuning. And then if you do fine-tuning, who's going to prepare the data, select what's useful, select sensitive versus non-sensitive data. Like all of that has to be solved. So there are a lot of challenges in how the technology would have to be adopted. The good thing, it seems like pretty much everyone is on board that it has to be used right now, right? People do see the value. It doesn't look like it's just, oh, there's a hype there and we don't know what to do. Like people had a general feeling that it would help them in certain different use cases. And then you go to different segments of enterprises, financial sectors, insurance, automotive, like they all see that there is a value for them, for that technology. But what's complicated is what the exact first use cases should be. And also after you narrow that down, how to go and implement it and develop at scale, because they never had an org typically that would be able to do this efficiently. Again, remember, they were AI first companies. So for them, it's a new toy. And they had some piece of an expertise, but not the rest. So a company like ours, CentML, is actually trying to close one of those big gaps for them. It's like how to build the system from our data. Essentially, we had foundational models, we had our data. Who's going to help us to milk the data and get the IP and get these models deployed at scale for us, such is also going to be cost efficient, right? Also, what we see is that the people that use it once successfully, I feel like they would never go back. They might criticize AI for being unreliable and blah, 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 that. But if, for example, you used $10 million before to find fraud in your organization, like say on the bank statements, and now you use a model to do this, and that model costs you $2 million. You're probably going to keep complaining to me as a company that's responsible for optimization why it's so expensive, $2 million. But you're never going to go back to $10 million expenses with humans ever again, right? You're going to try to optimize what you have, but you already know you make that step, there is no step back. Like you're always going to use some AI now, some form of automation, because you're never going to go back to doing this with humans, right? Because it has its own downsides. You start to forget when you use AI. And you say, oh, AI hallucinate. Well, the problem is humans also make up things and also hallucinate sometimes and also like make mistakes, right? So yes, there are challenges, but we need to admit what the challenges is. We need to build a good roadmaps for enterprises to adopt the AI, right? And I think the good thing that helps right now is that there are general consensus across many of these organizations that you need to be part of it. Your use cases naturally come in as you look carefully. It's not, you're not randomly pick it, you talk across the team, but you see where your data is, where your company unique proposition is, and you try to adjust it and help AI to enforce it, right? Almost all conversation we have right now with enterprises, like the first few conversations around, do you really want to do it? They are on board, right? That's actually relatively smooth. It's the challenge is what exactly that would have as the first step, because they never did it before.
One of the things I found is when you have a great software engineering culture, there's less of a problem. So, we've been on this journey from the individual lone wolf data scientist, and then we start thinking about ML DevOps, and we start thinking about joined up approaches for data architecture and data engineering and so on. And it all sounds great in principle. And then we start to build templatized ML DevOps framework, and we say, guys, everyone, you need to use this framework. We've got a team building it, and if you all use this template, then everything will be good. But of course, that doesn't happen because people tend to build applications just for them. So it's a real big step, isn't it, moving towards this centralized way of thinking and having functions and platforms. So, for example, if I'm doing pricing, I might have a team and it's their job to maintain this pricing platform, and it has a fixed API, it has a standard interface, and they just kind of, they make it really optimal, and it's kind of centrally managed. That seems quite a difficult step.
Yeah, so it's like I think when you talk about this managed platform, like a lot of people support right now, I think it's just a step. That's not a final solution. I don't think that would be, maybe I'm wrong, but I don't see a lot of people that just wants to use the vanilla llama for everything. I just like feel people, this is just a built-in block of the system, right? And I think those system would have many of those built-in blocks with a lot of fine-tuned specialized system to do what's needed. You probably need guardrails around things in each of these components. You need a lot of things. So it's way more complicated than just say, let's take a model here and then go run it and deploy somewhere, right? So in reality, I think what you need to do moving forward is you need to build an infrastructure that can run reliably those complicated systems, right? So essentially the system will be built out of multiple, say, agents, for example, and multiple different models with all the different constraints potentially connected to different databases of knowledge, right? Vector databases or something like that that people can utilize. So you need to build very different UIs for those systems where people can really plug and play components, play with them, test different things. Essentially you need to build you're not testing one model against another model, you're testing two systems against each other. So you want to put two complicated stuff one against each other and see how they perform. And the scenario is also very complicated. Remember, they're interactive. Things can be non-deterministic. Based on one input, you can conclude that one system is better than another. You need to get a very sophisticated environment tests on how the things behave. It's very easy to test. Oh, it's like how much faster it is and how much cheaper it is on a one metric. Remember, multidimensional problems are way more complicated, right? So you need to make sure that environment is captured properly, right? And you can, evaluate what's good for you, right? I think that's a very exciting thing to work on, and I think that the community would move over time.
Last time we spoke, you used the term dark silicon, which I thought was very interesting. What did you mean by that?
Oh, it's a relatively simple concept if you think about it. So imagine that you had a limited budget of the power that can you supply to a chip, right? But you have the ability to put way more transistors on that chip. So essentially, you have to live in the world where at any point of time, you cannot power all of it. You need to power only some of it. So you have to decide what to power, what not to, right? For a very long time, people were saying that we're never going to build anything like that. We're always going to everything that CPU was having, we're always building it, right? But then at some point, the end of, Moore's law and several other limiting factors lead us to a situation where Dennard scaling, especially from coming back to computer architecture terms, we're not able to keep the power constant as we improve their dimensionality of the transistors. Why is that a problem? It means I still, as a hardware company, want to sell bigger and bigger chips with more and more transistors, but I had not enough power to supply them. So either I had to make them bigger and bigger and bigger physically, or if I limit it by their physical dimensions of the chip and speed of flight and interconnects, I had to limit what I power. So essentially it has many different forms, like that limitation of dark silicon. Either you're going to reduce the frequency on how you run things. So instead of fully turning off some parts of the chip, you run it at like half the frequency, right? Or essentially we aren't utilizing the resources we have. I remember from my computer architecture class back at CMU, back then we're already talking about the phones and they being very power limited. And for example, it was very common on the phone where you had certain memory bandwidth available, but you can only use it for a very short period of time because otherwise you get power off, right? Like or heat. So there was a hardware there, but you can fully use it. So it means you need to become much smarter in how to use this hardware. That problem didn't disappear. The chips right now are extremely heterogeneous. Let's take, for example, NVIDIA chips, right? Like that is quite an interesting thing to look inside of it. With all the public information, we already know it has many different precision support, many different specialized pieces of it, right? So for example, even if you think about AI alone, you have FP32 precision, FP16 precision, right? That's combined together so that two FP16 can generate output for one FP32. Then there are brain float precision, there's integer precision, and there's a special dedicated units called tensor cores that don't use a vector instruction, they use like direct matrix multiplications in them. All of that is an independent unit. Most of the time, your software is not written to use all of it. What does that mean in practice? It means one way or another, a lot of those resources can be easily wasted on your chip right now. Whether you power them off or reduce the frequency, that's the choice that the computer architect who builds the chip has to make. It's a very tricky problem because the power becomes a limiting factor for many of these components, right? So yes, it's a very interesting problem that anyone who builds a modern chip has to deal with and prioritize one thing over another when powering on different parts of the chip.
Part of the problem here is that people are unaware of how much compute we're wasting. Why is that the case?
The first time in my life I faced it when I just finished my PhD and it was at Microsoft Research, right? And back there, I've seen a lot of people were excited to train a large model. We are talking about 2016, 2017, quite some time ago. People were using NVIDIA GPUs, but very old one, like Maxwell generation before P100. P100 was just built back then. And essentially, there was a lineup of people waiting for the chips. And I was like, interesting. And I'm an optimization guy. I was very interested in how well it's running because like out of a sudden, there's all these frameworks like, TensorFlow, CNTK back then that people were using. I was curious how well it's running. I got a permission and access and I profiled some of those workloads that people were running. I was mind blown that utilization is easily can be like 10%. And I came back to the people like, do you understand when you run those workloads, utilization of these chips could easily be only 1/10 of its potential. And they were like confused by what I'm saying because like for ML people, that was ridiculous claims. Like, what do you mean? Like GPU is running, it's busy. How it can be like not utilized? So this is the way of understanding and a level of abstraction how people from ML community typically think about compute versus other computer architect system people think about compute. So to this date, it's actually very difficult to get 99% utilization of the chip. Usually when you see that, it means like someone of these metrics is lying to you. It's just telling you some part of the story of what is possible, right? And that's a huge opportunity there to actually use all that, compute that is there. And part of that, there are many different sources of the waste. One of the sources of the waste is very basic. GPU is not even running all the time because you had a model that technically sits on the CPU and move the kernels onto GPU, right? And when you do this move, there are periods where not in the GPU yet. So you want to make it that it's properly pipelined and you're always on the GPU running something, but it's not always the case. Then another problem when you're running, you're not using all the potential of the compute available on the chip, right? because it has so much compute and the models are all flexible and different. Kernels are not always perfectly mapped to what you need, and that means there's a lot of waste there. So there are many different sources of waste. And even if you solve that, there still might be possible that you're only using one, like it might be your workload is just using one precision at a time or one compute units of one type, but NVIDIA might fully power the whole chip to run at full, like everything else, and you're just wasting that compute, not running anything through it, right? Yeah. So that's a very important thing. And remember, what is also challenging here is that when we talk about power limitation and dark silicon, if you actually make everything to run, you might actually overheat this thing because it won't be able to dissipate the heat as well. So you need to be very careful not overdo it and do it in a smart way, right? So it's a very interesting problem to solve, but that's where there are a lot of opportunities there, untapped potential that we at CentML in our company actually use for the benefit of our user. One example I really like to mention, like we get like one paper recently accepted around that will be out in a few months. Essentially, you can run your training and inference at the same time on the same chip. And the trick around it is just using all that gaps that's wasted and also use that different precisions that are otherwise not utilized. You essentially can run training and inference back to back. It's almost for free, right? It's possible, right? If you orchestrate the whole system properly around it. So it's an opportunity there. It's all this untapped potential that can be utilized.
Yeah, that's amazing. That's amazing. I mean, it's tempting to think that, we have these very high level abstractions, like even Python, for example. I mean, of course, a lot of deep learning doesn't run on Python, but as you know, Python is hideously inefficient. But by the same token, it's democratized computation, right?
Yep.
So many people can write Python code. But what you're talking about is a little bit more nuanced than that. I think you're saying that when we actually start to think of this systemically, when we have a big spooler and we've got all of these different workloads in this fabric, we can start to do optimizations that wouldn't have been possible if we were thinking of them individually.
Yeah, absolutely correct. And I'm glad you also brought up higher up the stack because because we talk about dark silicon, I started to focus more about the low level stuff, but there's huge waste is possible if you do things right at the top level. I remember when David Patterson, one of our scientific advisors, received his Turing Award. In his Turing Award talk, he showed the examples of matrix multiplication done in Python versus done in properly optimized in C++ and then optimizing all the way to the silicon. There were like 3 or 4 orders of magnitude there, the differences, right? So Python is very inefficient, but Python is very easy to use and develop things. It requires way less skills. So something that PyTorch and the Pythonic ecosystem was very efficient is that they hide all the things that require sophisticated computation from the running on the Python itself. Like you use that interface, but under the hood, it's running C++ libraries, and you don't need to worry about all that complexity is hidden from you. That is where's the beauty of it. It's like because ease of use is also very critical. Because writing everything in C++, it's not the way to go if you want to make that technology adopted by much wider audience. And even some of the inventions of our group and our company were around automated the compiler development. Like, for example, for many years at NVIDIA, people write very carefully crafted manual kernels to get the top performance. And that's considered the best way to go. But say several years ago, a lot of us realized that's not a sustainable way with AI. There's so many kernels and so many targeting hardwares, and all of that is very diverse. So we start to advocate, you actually do this more automatically using machine learning compilers instead. So in that case, you still need to give an input on what kernel you want, but use a Python interface to give an input. But the all sophisticated CUDA code under the hood, or PTX code even, is generated automatically, right? And it's feasible, and people are benefit from it right now. And I think people at companies like Google build XLA compiler that also does, some of those things quite efficiently, like in a more automatic way.
Now, this is one of the products that you have actually. So you can plug this thing into your PyTorch code. It's just another few lines that you need to add, and you can compile the model. So you can say, what optimizations do I want to apply? And it's going to make the model run significantly faster. Can you talk us through that?
Yeah, so it's like again, a couple of years ago where PyTorch ecosystem starts to evolve and starts to be more open to other people to contribute in the development. There was a possibility to use something called PyTorch.compile, right? So essentially, it allows to take your model as an input and use your own backend to optimize things. So our research group at the University of Toronto and then our company supported a new machine learning compiler, and they are called HiDat, that allows you pretty much within a single line of the PyTorch code to optimize it significantly. And since then, a lot of people start to go in this direction. Like one very successful project in this space is Triton compiler as well. So again, people realize that keep writing kernels manually is not the way to go, and you need a more automated way. I just want to remember to tell you, though, that this is just only a piece of the puzzle. This is we're talking about the kernel level optimization, not the whole model optimization. So then generative AI workload complicate this process even further. Why? Because they typically require something called dynamic shape, and compilers are not very good at optimizing something that has random boundaries. Like thinking about properly optimizing the loop that has unknown boundaries of the loop. That's very difficult, right? So essentially, that's what makes the life of compiler optimizers difficult, but it's still a solvable problem, and we also solve it in our company on how to run dynamic shapes workloads very efficiently, right? But that's at the low level, right? So why is it important is because that unlocks the ability of other people to contribute to the success of this PyTorch or any Pythonic-based ecosystem, right? And I think people realized that it's the way to go, and a lot of people contribute in the space. I think it's like right now it's very heavily supported, including NVIDIA, very heavily supports building this open source community around like machine learning compilers.
You know, like with C++, we have, you know, we have a handful of compilers, and if I'm compiling something on Mac OS, I use the same compiler every single time. But I'm getting the read that for machine learning workloads, it's far more heterogeneous. So there are specific optimizations for specific jobs. Can you explain that to me?
Yeah, it's a very important nuance thing. Like, for example, even like, first of all, training versus inference are very different workloads. Like people say like, isn't that very similar? Like, you know, like doing a lot of matrix multiplications, all of that. And the answer is yes and no. There are common kernels, but a lot of things that are very different between the two and the scale and all of it. Then it's also very important on and more nuance on how you optimize it for particular target. For example, your target might be latency, your target might be throughput, your target might be cost, or more commonly a combination of that. Then you had a bunch of tricks at your disposal that you need to kind of balance. And none of that is usually just make everything better. It's one thing sacrifices something for something. Like, for example, you mentioned today speculative decoding. Very cool trick, but there's nothing for free. So speculative decoding means you do something speculatively somewhere. It means you would have to burn that compute that you can use for something else instead. Why would it make sense? Well, if you want to cut the latency as one of the metric, so you want to speculate on the outcome, and you can maybe have something intermediate values ready for you to use, so you optimize it. But it means you need to burn some compute somewhere, and it might be actually burned for no reason if you actually run, right? So there is a trade-off here. So when you improve the latency, you would make your throughput worse. That would make the cost of the process higher, right? So there is no like free lunch in many of these optimizations. Another common example, people like to reduce the memory footprint of their model because memory bandwidth and memory capacity is one of the bigger limiting factors on running these models on NVIDIA, on existing chips, NVIDIA, AMD, or TPU chips. Then there are several different optimizations we can do to reduce the footprint, but none of them is completely free. So for example, you can recompute the values you otherwise need to store, but recompute means doing compute multiple times, the same compute. So you waste compute in contrast of memory. Why would you ever do it? Sometimes in some chips you had more memory and less compute, and that's a good, or the other way around, and that's a good trade-off. Or you might actually do compression, right, of certain parameters. Compression, lossless or lossy introduce other trade-offs. Quality of the model changes, and also extra compute associated with compression, decompression, but then it can potentially save you parameters. Each of these cases, and there are many, many tens of those different optimizations. And this is why it makes it hard. Like for every model and for every use case, the optimal Pareto frontier might change dramatically, and you need to find the way to what would be the best set of techniques to do it. And it's very hard to do it fully automatically for every new model, for every new workload, for every new chip that you have at your disposal. And this is some of the inventions that we push through in both research community and as a part of the company. We say that has to be done more automatic, right? Because a lot of early solutions were really hard-coded to run on a given model on a given hardware. In reality, it can be done in more automatic fashion. So it means that the customer brings a new model quickly. You can do it quite well. For example, I'll give you one example that I think highlighted what we were very proud of. Last year, when Llama 2 went out, a lot of famous companies were like, oh, we need now optimize our models to run it efficiently. And it took many, many weeks for some of them to do it. It took us less than a day to make Llama 2 to run on our software stack because everything is a very automated process. Again, this year when Llama 3 was released, 405 billion model, we did a live hackathon. We didn't have partnerships, unfortunately, with Facebook and Meta on that. So we didn't have early access to the model, but within 1 hour, it was working for us, right? Why? Because everything is automated. We anticipate certain characteristic of the model. We know how big it can be, and we were prepared certain trade-offs. Then we found the optimal mappings, and then we just, make it available to people pretty much immediately. And that's very important when there's diversity of models and diversity of the workloads is changing. Another very important factor specifically about GenAI is that even if the model is fixed, the input itself can be dynamic. You change the sequence length, all the other different hyperparameters. There are many of them. That changes what's the best way to map on the hardware. So I like to show in my lectures that for a basic attention block, depending on which parameters, how big is sequence length and the window and other parameters, you might actually want to fuse these kernels instead of these kernels and slice it this way or other way. It's a very complicated problem even for humans to find it. Obviously, you don't want to do this manually every single time when someone changes the input of your model, right? So this is something that a compiler has to do to make it efficient.
Yeah, you've articulated that really, really nicely. So what you're saying is that this is very situated. We're in a non-stationary environment. There are many moving parts. So, we might have different batch sizes, different input sizes, and so on. And also we might be in the context of a system. So we might have this big cluster that's doing all these different jobs. And that actually gives us a whole margin for optimization where we can select the correct optimizations and the correct kernels to use and so on.
You're absolutely correct. So there's all that complexity in there. And this is why when we talk about enterprises early in this talk, remember, it's just hard for them to do it because if you do it manually, you need very, very, sophisticated engineers that know how to do it. It's expensive for them to hire these guys, right? And it's actually not required because it can be replaced by the software, right? This is where all that complexity comes from. It's the workload itself is so dynamic, so complex. And as you said, the system itself has all these external components that are moving. So you want to make sure that this whole thing interplays really well. So you optimize for not a particular benchmark, not a particular model. You optimize for this use case for that customer in that environment they're running right now, right? And this is why it has to be more dynamic. And this is why you need to build the system stack that it would be able to adapt with that complexity.
Yeah, it's a bit like the no free lunch theorem applied to machine learning optimization.
I agree. Yep.
We were saying that we now have this new paradigm of model development where we have this big compute fabric. We can do a whole bunch of optimizations against that. I mean, who are your customers and how is this working?
Yeah, so so several of our customers, enterprise customers, for example, Deloitte is one of them. And it's one thing that's important at this stage right now is that, in my opinion, you really need to build this relationship together with the customers. For them, they never actually had GenAI in production before, ever, right? That's the first experiment for them. There's certain expectation, there's certain knowledge in the team, and you want to make sure that we augment their team knowledge with everything we had external. They best know their workloads, right? They best know their data, and they had an understanding roughly what they want to build. We had a very good understanding how to build the system, and we have some understanding what data they might have, and we are trying to build that bridge. So if you say me where the challenge is how long that bridge takes right now. Building that bridge with an enterprise customer, because a few of these enterprise customers, they're more like partners to you. You spend a lot of time, you nurture this relationship, they might become your channels, and we're building multiple of those. And right now we also had another customer called Redapt, which is one of their biggest Dell hardware resellers. And again, they had the hardware they built, and they want to make their hardware LLM appliances. And they had accelerators like NVIDIA GPUs there, but not necessarily H100s or A100s, like smaller GPUs. And they want, like magically, that these boxes out of a sudden starts to run like all the LLMs that people are using H100s for. So someone has to find all that new transformation and balance them out so it worked for them, right? And it's not a trivial thing because like these boxes not only had smaller GPUs, they also don't have fast interconnect like NVLink. It means you need to find how to communicate with less data, making sure that all of these smaller chips that are cheaper and smaller, but also less compute and less memory, are busy and doing useful work. And then you get the output and the speed that you actually good enough for the real use cases. So we get a lot of this chat with your data interfaces for the companies like that. Another similar use case for us was a company called Arcadis, right? It's an engineering company. It also had multiple, boxes with GPUs and want to make them use in LLM and RAG scenarios. And that's very common. We also had multiple different ongoing partnerships with big vendors like GCP and AWS, where we help them better utilize the compute, unlocking their own customers as well. So this is all ongoing. And ultimately, it's right now when we talk about enterprises is the time that takes to go from research to the real adoption at scale. That's important because there is a wrong perception sometimes by data scientists is if I found some really cool model somewhere online and I'm running on this few inputs and the quality looks cool, I'm ready, I can go and deploy it. It turns out, no, that the tool you use to deploy it might work on A100, but it won't work on large scale cluster, like operating like that. And you actually didn't optimize it by running other workloads and didn't realize the way you run, you can only run one input at a time because you exercise all the memory right now. And if you run one at a time, the price running it is like enormous and it kills the whole point of the workload or the use case to begin with. So you need to educate the people, say like, no, you need to be careful about that. You tell us what the constraints are. We help us to do it for you. We try to automate this process as possible. For us as a company, it's very important not to become another service company, right? That's what I'm trying to avoid. We do this initially in some of this engagement, but for scalability, we try to automate this process from each of these new engagements, try to make sure that it becomes very repetitive. So we had several other GenAI startup companies like Echo AI, for example, and a lot of other conversations where that learning process with the bigger enterprises help to fully automate the process. So when they arrive, we give them all the software stack and they can use it out of the box with no any special features needed. So that's another interesting thing. There's different segments. Some require some customization, but some are like fully automatic. And where it's fully automatic, it's cheap. It's cheap for them to use us and also cheap for us because it's very easy for us to onboard customers like that. It's because it's fully automatic, right? We can support a lot of that. Why is it important? It allows us to keep very low prices for them, for our software stack, because we don't need to use engineering time extra for that, just a basic support. So it also means that they can be successful because their software stack building on top of the model is not that expensive for them anymore.
Yeah, I agree. It's good to avoid the consultancy trap, but of course, you guys want to build this massive platform. You want to scale up, and there's always this tension between, kind of focusing too much on individual installations. But what is your relationship with the cloud providers?
Yeah, as I mentioned, we had a very good partnership with several major cloud providers. So, obviously, notably, it's GCP and AWS. We're officially partners with each of them. We're on their marketplace, and we had several strategic engagements with them directly with the engineering team, and also with some of their customers as well directly. Then we also had different stage of engagements with other cloud providers. You can think about all the usual suspect in the space. I'm not going to say until we publicly announce it, but there are a lot of those conversations. A lot of them are looking at the software stack built on top of their hardware. A lot of them had very good expertise in how to build, cloud service, like how to provide that bare metal access to their hardware. But they want distinguishing characteristic. They don't just want to be bare metal supplier, right? It's a very competitive market right now with margins for their hardware going down and down. So they want to have a software stack that would attract customers and keep them on the platform, right? So that's a very important thing right now. And we help them to get good use to bring the customers and connect them with their level of expertise, because majority of them are not like bare metal experts to use, their hardware directly. And you also try to help them utilize their hardware better. So they would understand there's like, you can co-run things together and you can do this and that, and you can save a lot from your compute that you didn't even realize is possible.
Interesting, but you don't feel that you're competing with them in any way. I mean, I guess this comes to the moat question. But let's say if I don't know, if AWS gave you $5 billion to be exclusive on their platform, would you be interested?
Well, $5 billion is a lot of money, right? Like it's like it all depends on the stage, right? If the deal like that will come, we'll talk. But like honestly speaking, we always try to build something that would be not overly specialized for any cloud provider or any particular hardware even, right? Like we always wanted to have a platform where all cloud providers are equally represented and all the different hardware equally represented. And I think it's very important for us overall is because at the end of the day, we want to get the best performance for the lowest possible cost. And we want a place where we had an honest opinion and that would optimize my workload for my model and for my use case and map it the best possible way, right? And I think for that, it is important to be in good terms with all the key cloud providers and all the key hardware vendors. This is why we had a very good partnership relationship with NVIDIA, and then NVIDIA was our investors in our previous round next year. But we're also like working with Google, had TPUs. We're talking to AWS, has Trainium chip. We talk to other vendors. Like we are trying to be equally friends with all these companies because I think they're all important. And people don't want, I think in most cases, one dominant monopoly of some sort. They prefer to have a choice of multiple things that makes the market also more healthy, right? So I think we are trying to help them to find the best chips, optimize it with whatever constraint they have. And they had any constraint, they have older NVIDIA GPUs and they had the new advanced AMD GPUs. We try to make sure that they can leverage everything that they have at their disposal.
Interesting, because there's always the question of like being in a sovereign cloud or being kind of like, embedded in one cloud. But I suppose you could go one level of abstraction up because it's great that you have this agnosticism to hardware. So you have this incredibly intelligent system that can optimize for the hardware that is running on the cluster. But could you in principle do that at the cloud level as well? So you could do cost optimization by setting up clusters, this bit on AWS and this bit on Google or something like that?
It is technically possible. We already do like multi-cluster things right now, like within one vendor, but it can be done across vendor. It's in principle can be done. The problem is the communication between them and how costly it is, like inbound traffic and egress, that can be expensive, right? But technically it can be done. What at the beginning, you raised the important questions, like how you integrate with all of these different infrastructures. And I want to say that there is some level of complexity, but not dramatic, because ultimately we pick a level of abstraction at the level of a container, right? So all of them support containers one form or another. That's a very basic concept. So we make sure that whatever we deploy is just based on the concept of container, and we can build on top of that. That means that we can easily go between GCP and AWS, and then all the other guys that are bare metal, they just need to support, let's say, basic Kubernetes on top of their infra, and that's good enough for us to build on top of them. So it's really a few specialized cloud providers that is like a hyperscalers, and everything else from our low-level perspective, others are more or less identical. They're all like bare metal access, and we can manage, them quite well.
Yeah, I think part of the thing as well is you need to have this pragmatism because you need the models to be close to where the data is. So, for example, I think you're built into Snowflake. And from a database query, you can actually call into the cluster and you can say do some sentiment analysis or something like that. But in order for these architectures to work efficiently, you actually need to kind of respect the data architecture boundaries as well.
Yeah, you're absolutely correct. And there's you brought up this case, yes, we partner with Snowflake as well. And we are available in their marketplace, so we can accelerate the models that the customer wants. Why we would do it? Because there are people that are really like Snowflake infrastructure, their data is already there, and they would prefer to do things closer to where the data resides, right? And not moving it necessarily to the cloud, like a different cloud provider. So we provide them that flexibility where they provide them the ability to run whatever model and whatever applications built on top of the standard ML models where the data resides for them. So that's where it's convenient for them.
Cool. So moving over to the agents discussion.
Mm-hmm.
Now, I'm very excited about agents. I think don't get me wrong, I'm not excited in a kind of, it's AGI in the singularity kind of way. I'm just excited in the way of, I love building, distributed asynchronous systems. I think it's very exciting. I think it's really cool to think about these little like asynchronous units of computation at the application level. But of course, using a shared computation fabric, which you guys are doing. So how do you think this paradigm of kind of software engineering is going to change things?
Yeah, I'm definitely with you. And I also like to build distributed systems, a synchronous one. It's very exciting that it's open up. Again, going back to the event I attended last week, Intelligent Applications, it was a very nice event organized by Madrona, AWS, and Microsoft. And it was clear a lot of people, they were running around saying how about agents? What are you guys doing? What are you doing in that space? Everyone is excited about it, similar how they were excited about RAG, say 6 months ago, right? But it's you want to find this killer app where it's used. So the problem with this, it seems like it's one challenge is that it's not used as heavily in production as we would hope to. So it's a little bit early. Another thing, people, when they hear a nice buzzword, start to use it for everything. So whenever they say an agent, it becomes almost like a synonym of any application. So it's not very helpful. You need to understand what kind of intelligence you encapsulate and what you mean by an agent in general. But I do think this is the direction we should go. I'm not as excited if all the future we're going to use GenAIs by running individual models here and there, and they still talk. If you have human in the loop, it's not very efficient. I want the system to be able to communicate and exclude the human in the loop, and human being a designer at the top and overseeing the process, but not overlapping into every single conversation. It's the same as managing a company. It's if I, as a CEO, have to be in every single meeting just to orchestrate the communication with everyone, that's a failed company very quickly. It's I rely on them to have the proper meetings protocol without me and being efficient. I don't need to be there and not being a bottleneck. It's the same here. It's very interesting how to build this sophisticated system out of those agentic systems, right? It's exciting. It's still a lot to be proven on how it will be used in real examples. Remember, people talk about fine-tuning, and fine-tuning was used to a certain extent, but it didn't solve all the problems. It turns out that fine-tuning for these models is also not very cheap, right? You still need hundreds of GPUs in many cases to do fine-tuning, and you need an expertise to do it. So a lot of people say even fine-tuning might be too expensive for me, right now. Then RAG came up, and it helps with certain things, but you realize that RAG without fine-tuning is not as good as RAG with fine-tuning. So people look at it helps you with certain things like guardrails, but not with everything. But we anyway seen the real use cases where people benefit from it. But not of that concept alone is the answer. It's just all pieces of the puzzle that can benefit depending on the use case. But then ultimately, with all this concept, you're building something more exciting and that become agents. I think everyone starts to talk about this agentic system. I lost track how many startups are around claiming that and fundraised recently around that space. But again, I want to see a customer tell me that I'm actually building it, then I will be excited. Remember, we talk about enterprise customers. These guys always going to have certain lag of adopting things. So I don't see them adopting agents yet. It would take some time. And I think we as a company, CentML, need to be ready when that comes. And that helps with us interacting with these GenAI startups because they are the driver of that novelty of that technology. But ultimately, the revenue and the future of that technology and the use comes from enterprise adoption, in my opinion, and cloud providers adoption. So it starts to be used there. Right now, I think a lot of that is just an experimentation phase. And I talked to a few companies that are doing agents, and they say, guys, do you need our help? Do you need optimization? Is it at running at scale? They're oh no, everything is few requests here and there, and we are calling ChatGPT under the hood, or GPT, OpenAI API here. It's oh, obviously it's not at the scale where we can help, for example, right? I think generally it's not. It's they're just proving that something can be done. It's an important step, but it's not the scale step yet.
But still, I'm a big fan of your kind of methodology, which is that, let's say I've built this big distributed asynchronous system with the actor pattern, and I'm looking at the logs. There's a logging actor, and you can start to see patterns which can be optimized, which you wouldn't have been able to do before. When building these AI applications as well, what I've noticed is that part of the blocker is the complexity grows very quickly if you try to do it monolithically. Even if, like with a RAG system, if you're building an information retrieval system, typically you're kind of like sticking together, query auto-completion systems and then re-rank systems, and you're talking to all these different heterogeneous data sources. And, the footprint of the thing is very complex. It's very difficult to monitor it and deploy it and so on. And the reason why people don't use, let's say, the actor system is because I guess from 0 to 1, it's actually more complicated. And, when you look at Twitter and LinkedIn and all these big globally distributed systems, they're already doing it. So it's almost like we need to say to people, okay, you need to start by building these distributed systems. I know there's a bit of a learning curve. It's going to take you a while to get there, but you need to do that. Clearly, though, we need to come up with a new abstraction. I don't know whether we could have a new type of programming language or some new way of building these systems. I mean, what might that look like?
Yeah, so I think there are several different directions we can go with that. And I've seen some attempts to solve the problem. There are definitely people at Berkeley I've seen working in this space, and Databricks working on compound systems that I mentioned before. It's very promising. I talked to a few of my graduate students also as one of the next interesting big problem to work on. So I think we would need not necessarily a new programming model, but we need a new level of abstractions to work with the systems. And you're absolutely correct. We not only work, we need to identify things. We need to be able to monitor and debug them. Like, remember, as with all of the system, like, you're never smart enough. If you build it, the system as good as you can, you're never smart enough to debug it, right? So that's a conventional problem. It's it's not only a matter of building it. You're going to build it with issues, that's for sure. You need to be capable of and then monitor and debug it afterwards. Everything that is asynchronous distributed is always difficult to debug, right? Making it deterministic, it's a known problem fundamentally from the auto-parallelization efforts we had for many years. So essentially, we need to make sure that we build that as a part of the system, that they are scalable, monitorable, profilable, and we can debug them with reasonable pace. All of that is still an open problem, right? I think some of the things we learn from building classical distributed system would help, but ultimately there are going to be new problems there. First of all, I believe those systems are going to be very, very heterogeneous. So I believe there's going to consist of running things on CPUs, GPUs, other accelerators like TPUs, and other components, because it might turn out each piece would run in different environment, right? That particular model might reside on this cloud provider and things like that, and you need to orchestrate all of that. So it would be like building software that has to be orchestrated across the globe type of thing, potentially running in different cloud environments. You also want to make sure you build smart version of migration, right? People work on that for a while in CPU world, but now you would need to do this at, an AI space. So you need to make sure you had checkpointing mechanism, different, a lot of things are needed to make sure to manage that complexity. It's a very open, interesting problem. It's very interesting to build products like that. It's also very interesting for any future, graduate students looking for projects to work on. That's a very promising area, in my opinion, right? A lot of very exciting things will come up. And I'm only touching the system level aspect of it. I'm sure there's a lot of excitement on the AI space on what can be built with things like that.
Yeah, indeed. And of course, there's no such thing as a free lunch. There are always bottlenecks. But I love that book, The Mythical Man Month. And it was saying, even if you have a perfectly partitionable task, you still have this kind of curve, right? At some point you can just add more and more developers to the problem in it, and it doesn't go any faster. And I'm sure there would be similar bottlenecks, but it's still cool though, just to have a whole bunch of engineers that can work on different units of the system, and they can work independently and they can deploy independently, and that's very exciting. But I wanted to move on to the MLPerf and ML Commons. So now you're a founding member of MLPerf, and the research co-chair at ML Commons. Now this is all about benchmarking in AI. Can you tell us about that?
Yeah, so what was the motivation to, first of all, build MLPerf before it was even created? So my own journey was like that. So I was, as I said, at some point here in 2016, I was at Microsoft Research, right? And I want to understand the problem of utilization and how well these workloads are running. Because I had a theory that the guys are running a lot of those experiments at scale, never actually built sophisticated systems themselves, so they never looked at that. And it turns to be true. And then the second problem back around 2016-17 was almost everyone claimed back then they're 1000x better than everyone else. And when that happens, you know someone is cheating, and majority of cases everyone was cheating, and they were cheating because they're using different data set, non-traditional methodology. A lot of things you can cheat around the system. And we've seen this before. The world where was an explosion of CPUs being built in 70s and 80s, at some point got a benchmark called spec that helped to build it. And there were people that clearly built it and had this experience. So I thought, okay, it seems like that benchmark doesn't exist. So when I started my academic journey at University of Toronto, my first 4 graduate students all work on building benchmarks for ML, essentially. I said, look, I'm a systems guy. I want to optimize it. I can't optimize it until I know what's happening. I need to know what the things we can do right now and what's problem, what's not the problem. There are models, there are different data sets. I don't understand. Everyone claims ridiculous things online. It cannot be true. So we start to work on that, and we released the first benchmark suite called TBD. So it was training benchmarks for DNNs back then, but also it was called TBD because the models were changing so quickly. Every time we finish an iteration, there's a new model there that has to be excluded. So it was always to be done. So we called it TBD. I think it's still like the website is still alive, probably somewhere. So we're making this TBD suite available to the public. And in parallel to that, I was talking to my friends at Google about potential collaboration on different research topic. And I mentioned somewhere among other cool things I'm doing, like, oh, I'm doing this benchmarking for ML. And then one of the guys there, Cliff Young, who is one of the architects of TPU, said, like, that's very, very relevant. There is something that happens between us, Baidu, and Stanford that's not announced that we're talking about, but like, you seem to be a good fit. Like, do you want to partner or want to do it on your own? I said, like, oh, I was open to partner. I didn't know you guys are doing this. So this is how I got into this thing. And then after a few months of emails, there was a first meeting at Stanford, right? Back then it was pre-COVID, like we're talking about 2017, 2018. So everything was in person. So I fly in there very regularly. And then we just meet in a small group where I try to identify like what that benchmark should be. It's a very different workload from a traditional CPUs. It's very different from anything else the world benchmark before. The scale is very different as well. And there's training, there's inference, there's so many different use cases. There's like large scale, small scale. There are so many categories. It's very hard to pick one particular thing to measure. So we sit down and start to build working groups, start to build methodologies. Several of you early benchmarks in MLPerf were built by my graduate students, right? We contribute one of the first speech benchmark, like based on the deep speech. And a lot of that was done at the beginning by the academic community. There were people from Berkeley, like people like Dave Partison were involved. The people from all the industrial companies you can think of gradually start to join. So it started by about maybe 15, 20 people in the room. And now I think MLCom, I don't know, thousands and thousands of people, many of the work groups, like it's just an avalanche of people. Rather, it was half at the beginning, academics versus industry, but obviously when it starts to get traction, like it starts to be over-dominated by industry. Now it's a huge organization, right, that does a lot of good things to people. It provides that proper measurement, step to say where you are. You cannot come right now and say, I'm 1000x better than NVIDIA or Google. If you claim that, go come to MLPerf and benchmark, and ML Commons will release the results. You really want 1000x. And usually the answer, no, you're like cheating somewhere, right? So right now those claims gradually disappear, and essentially people are not claiming this anymore. Like people know what reality looks like.
We've got this big problem, don't we, in benchmarks, that they don't represent real-world usage of the thing. I mean, it's been spoken about Kaggle, it's been spoken about MMLU and LM Cicerina and so on. And, how do you, and of course, benchmarks get good-hearted as well, which is that when they become a measure, they cease to be a good measure. How do we actually make these things faithful?
It's a very hard problem that people try to solve for decades. The question is, can you make them perfect, or you just want to get them reasonably good enough for the purpose they are reasonable? So essentially, when we build MLPerf, we know we cannot make it perfect. It's too complicated of a problem. But we try to make it sure reasonably fair, because the rest, alternative was a wild, wild west that exists online back then, where everyone claims that we're better than everyone, and potential customers were all got lost on what can be done. So essentially, what there are all these benchmarking crimes that you can do, and it's the choice of the company that present their benchmarks and how honest they want to be. So we create the rules that their playing field is reasonably honest. Like, for example, for training, very early in the day, we realized that some company has way more resources than others, so they can win in convergence just because they had better hyperparameter tuning, and they can spend millions of dollars in advance, find the right hyperparameter so they converge faster. So in order to make things more equal, we said, like, look, if someone is doing that, others can steal your hyperparameters and the intermediate round of result submission. So if you ended up using this, if say you are like a big company, a hyperscaler or NVIDIA, and if you do that, it's okay, it's totally legal based on the rules, but others can use the same hyperparameters that you do. So we try to equalize the playing field as much as we can do. Obviously, the big companies like NVIDIA and Google still have way more engineers to do the manual tuning. But at the same time, it's important to make the field as equal as possible for people. This is why we'll think we're very successful in MLPerf. You have big companies submit their results, and small entities and even academics can submit some of the results, right? Again, it's very far from being a perfect, but it tries to keep up with what's going. For example, this MLPerf has Llama 70 billion parameter for inference. That's not the best that Llama has to offer, but the next MLPerf, say in the February, would have Llama 3 with 405 billion parameters, right, as an inference benchmark. So the goal for MLPerf was never launch the state-of-the-art, fastest and available best model, but something that being perceived by the community as a stable status quo, like the really, really good model. So it means that by that time, there might be another Llama around, but we still benchmark the chips and the software stuff that's something that is really reasonable, right? So no miracle there. We don't solve all the benchmarking problems. You can still overfit things, like you can still put, say, 100 developers and manually tune to get just great results on these models. And then a new customer come to you with a very different model and they get very poor performance. This is on you as a company, right? Like we cannot stop that from happening. But we create an equal field for people to demonstrate result on a representative set of the models. And that ability to do performance cheating is getting harder and harder because there's so many models across different benchmarks. Good luck doing this manually. You need like hundreds of engineers to do it.
Yes, I mean, you spoke about, reproducibility, leveling the playing field. The good heart thing we kind of spoke about earlier before, because you could optimize for accuracy. We tend to optimize for headline metrics, and then maybe we lose something on performance. But have you noticed that the diversity of submissions has actually kind of influenced the evolution of the benchmark?
It's definitely the case. Like, I'm obviously like running a company for more than 2 years, so I'm not as closely working with MLPerf as I used to be, but I clearly see the community is growing, and it creates a lot of different camps there that people do an algorithm, that people even start to do, data benchmarking specifically for ML. People are doing storage benchmarking, like all the different aspects of the system. So, and they're separated in different working groups. That's how you manage the complexity of so many people involved. And I was involved in several different groups at different stages, and obviously was helping with research and promoting MLPerf on the academic stage. And I think it becomes, like, if you ask me whether MLPerf and MLCom are successful, to me it is, and I'll tell you why. Like, every time right now you see the announcement from NVIDIA, from Jensen, about like their new chip, it's like what the numbers they're citing. That's what they're citing. They're not citing any special numbers that they got NVIDIA. They're citing the MLPerf results, right? And there is a good reason for that, right? Because that is not just measured by NVIDIA. That was validated by their peers and competitors. It's not perfect, right? But it's still someone else go and look at your numbers and they can reproduce and run what you're doing, right? To an extent. So they can see that you legitimately get these numbers and they can see where it's coming from, right? So yes, and all the tricks become public and actually push the science further because like all of that is visible for the rest of the world. It's very important. It also make effect on the fate of the company. I remember there was one example where one of the ML hardware startups decided to participate. And they had a very good chip, but it turns out to be not as good as some others. So they bring up their solution and the results were not great. And the investors then said, oh, we're not believing that anymore. They took the money away, right, gradually, right? So it is a powerful tool, right? And it's a more honest tool because like before they wanted telling investors that they're better than everyone else, but now they came and measured and they've seen they're not. They may still have a good system, but they will say 2x worse than say something like Google TPU, and because of that, they just like it's not something that was proceeding as actively. So that's very important because otherwise it's very hard to validate all these claims of how good performance you have and like what kind of a system you have. I think after that, the number of BS online about the performance reduced dramatically, right? Because if you claim like that, people said, go to MLPerf, validate your numbers, right? And you have, like, if it's so good, why don't submit it? Why don't make it visible? And even before people were open sourcing things, but when there is open source things, but no proper methodology, it doesn't matter. Like how many different ResNet results we had with different data set that claimed ridiculous things around the performance, and there was always some methodological cheating. Here, everything is under control, right? So like we limit the amount of variables that you can cheat around. So we get you all the optimal parameters that you can pick, but you can't cheat against others with those parameters.
So I wondered what your thoughts are on the state of industry research. Now, we were talking about this last time that, Noam Brown tweeted, and I think he got into a bit of a spat with Jan LeCun, but he was kind of saying, look, we've actually got millions, or even maybe more than that, millions of users using our stuff, and as an academic, you've just got to convince an area chair and two reviewers. But how do you kind of contrast the kind of industrial research that you're doing versus academia?
Yeah, and it's like all my life I like to sit on the both sides of the fence. I'm very glad that my family also supported me with that because it's actually taken a toll on you. So there is a reason for that. So there is a benefit of being in academia because you work on clean, nice ideas without any industrial biases and the immediate deliverables, right? Remember, in industry, we're all at the end of the day, we are for profit. We need to generate revenue. A lot of decisions have to be based around that. And it's good and bad at the same time. In academia, we're solving problems, right? And we are usually very honest, or we're supposed to be very honest in how we do it. And yes, you can criticize the academic system, how you select the papers, but that depends on the community. I actually belong to the systems community. And like in some of our top conferences, in order to get in, you need to get 5 to 9 reviewers to accept your papers, right? So it is actually not that random as it might sound, right? And the bar to get in the top conference is actually quite high. It's very different from a ML community that had tens of thousands of submissions and thousands of accepted papers, but that's part of the difference between different communities. So I think it's unfair to say that everyone has necessarily a low bar of accepting the papers. But it's very important because the innovation comes from them. Remember, it's not really the industry that invented a lot of these advanced things, like deep learning, a lot of those things were invented actually academically because academics thought it has the potential, they believe in it and build it. And they didn't require tons of resources to make it work at the beginning. The industry is very good at making it at scale. So when people realize what the deep learning potential is, Microsoft Research, Google, OpenAI as an example, starts to scale the technology. So like Google, for example, is behind attention models, right? Invention and BERT. And then OpenAI took, a lot of that and started to build further and further and scale further, right? So that's a good thing that industry can do. So the industry was always important because I believe in academia, there is this fallacy you can go into solving an irrelevant problem. You become like a pure mathematician. You just pick up a random problem that looks fancy and you just solve it and publish a paper. I never liked it myself. That's something always bothered about me. I always want to be close to industry because these guys have the right problem to solve. This is why always in my career, always at least one hand with one leg, whatever the right way to say it, was in industry, right? because I want to understand what the real problems exist there, right? And that's the way to contribute. And then there's evolution in some of those things. And an industry usually have the right problems, but they not always have the time and engineering focus to solve the right problem. They solve what's needed for their customer or for the next deadline. And this is why for many years I was always taking the problems from industry and solving them academically, right? And then I had to move do the focus slightly differently, because I realized the solution I came up to the problem that exists in industry, I cannot scale to the enterprise quality in academia. That's the limitation of academia. Like I can hire 20 graduate students maybe, but I cannot hire 50, and they're not going to generate the code that's needed. They had a different goal. They had to publish their papers, to get their PhDs and master theses, rather than actually building artifacts, right? We do a little bit of artifacts, but so it's a very tight interplay. So I reached the stage in my career, said like, well, I built something really interesting, done it, now it's become practical, and I realized that if I don't do it, like others like kind of ignoring me, they're thinking it's not important. So I think I'd better build the company and do it the right way, right? And remember, that was all the pre-ChatGPT. So it's very nice interplay between the two fields, right? And I think both need each other. So it's not like, oh, research lab, like people between research labs very frequently move, right? I always like to think that we need to have also one of these best leading labs in the world, like Bell Labs was at the time, and AT&T Lab. Like all these labs were like a place where the brightest, graduate PhDs want to go and develop new stuff. It's always nice to make sure that we have something like that. And Microsoft Research was like that for a while. Like I want us to have something like that moving forward as well. I think I would hope that someone would pick it up. I think Matter did it to a certain extent with AI, right? And Jan LeCun pushing a lot of really cool stuff there, like in the AI space. But I think I would love to see this more beyond AI as well, like in other areas as well. I think that's a very important interplay in between these two areas. And I think I spent all my life, being either on one side or the other, but always staying connections with the other side.
And what do you think about the trade-off with exploration and exploitation? I mean, I always feel that there's a bit of a basin of attraction. Even, Sarah Hooker called it the hardware lottery. And I suppose that's kind of what we're talking about now, that so much of the deep learning revolution was just kind of influenced by the investments and research in hardware and so on. And you can just build this whole directed acyclic graph, and we can do a bunch of graduate student descent on top of that. But, do you think that just having a few random people working on completely crazy ideas might lead to something?
You need to select those crazy people carefully. I think you need to have some of that. I remember, there was a reason why Jeff Hinton, who actually won Nobel Prize today, right? Which is,
oh yes,
a great achievement for everyone, who knows Jeff, and Jeff obviously personally. But again, talking about that, for example, some point, in US, they just didn't believe in this whole field of AI, right? And I'm glad there was a country like Canada that actually was willing to invest their people with this crazy ideas that is feasible, and see the potential in that, and believe long enough until they can reach the stage that actually practical, and out of a sudden it change the world, right? So you need people like that. The fundamental research has to be there, but you need to also see where it's there is a chance whether this is just a crazy person, like you can't just give everyone, there should be a selection process, and there is you select the people that have the chance to change the world one way or another, and give them resources to make this happen. Whether there's grants exist, this is why industry also give money into research grants and give us the chance to innovate, right? I received some of those awards from Google, Facebook, and VMware and others. It was also very helpful to advance your research in the areas that otherwise you can't afford because you had the budget, right? But in terms of exploration, exploration, I think it's a very good problem, general, and I think there is even resemblance about what we have in ML space right now. I actually think about spending money on training is exploration, and using inference and deploying as exploitation. And for a long time, I was very puzzled that we were mostly doing exploration without no exploitation. I was like at some point that has to change, right? People has to start to actually deploy those models. And I'm glad to see that starts to happen first, at a reasonable scale, starting last year, but also very significantly this year. There are clear trends I see in NVIDIA reports and others that people want to deploy more. And we reach the stage where, yes, the pre-training is probably only can be done by a dozen of companies in the world, and fine-tuning maybe by a few hundred. And the rest of the world is going to use like the fine-tuned models and, RAG and like building on top of that. And it doesn't limit the creativity, right? It's still actually a good thing for the world. But I think like someone needs to say like enough is enough. We don't need to retrain 10 times like the same thing again and again, and things will be done in a more incremental way.
Imagine going back in time to the 1980s, and I think Hinton was in Toronto even back then, right? I'm not sure when he moved over there, but imagine saying to him that all of this stuff you're working on, he would have been kind of intrigued that we're having the opposite conversation. We're talking about graduate-student descent, inevitably on deep neural networks, and imagine telling him he was going to win the Nobel Prize. That would have been amazing.
Yeah, especially if you tell him you're going to win a Nobel Prize in physics, he probably would be puzzled, right? Yeah, but it's like. Yeah, but yeah, it's an interesting, like he was always a strong believer as far as I know in what he built, like it was evident from his whole career. But the scale of it, I feel like it's even impressed him, right? Like it's just Vera. And I think he had, like last time I talked to him on one of the flights from Toronto to San Francisco, like he had very serious concern right now where it can go with these 8 years, because it seems like those models are improving at a very rapid pace. And we need to also be very careful about where they can bring us. So he had a very valid concern about how powerful it is, right? So it's a little bit like the story, Oppenheimer was like a nuclear, bomb, right? An invention, and then not being able to control it, right? So it's again with AI right now. Right now it's in the hands of the world, right? You contribute, but you have no control. You can't say that's a concern, but you need to convince others you don't have a control over the technology. And it would never become what it is if you don't make it available to the people. But I think that has to happen one way or another. Like it's just like might have been happen later, but it has to be invented. It was asking for it. Like we need to learn. Like we were looking for a way to learn differently, right? And that was imperative to have something like that.
Yeah, it's interesting the point about Hinton's fears. In a way, no one disagrees. I think everyone agrees that this is transformative technology and the world will never be the same again. I think people on the left think that it's kind of changing, it might be it's reducing our agency, or it's kind of dramatically changing society. And of course, some people think that it might recursively self-improve and become super intelligence or something like that. But everyone seems to agree that this is a very dramatically transformative technology.
Yeah, it's hard to argue about that. It's like for a long time I was asked like those questions like, do you believe if it's just hype, is it another bit mining, or is it a real substance there? And said like, look, like everything as a scientist I know there is a real substance behind it. Yes, hype is always on top of it, but there is a real substance. And now, yes, I agree with you that it's really transformative. We are never going to be the same, right? You can't just forget about what we learn or we're able to do with this technology. Tell it to all the students that use ChatGPT to pass their exams, that it doesn't exist anymore. They can keep memorizing things that like they're not going to go back, right? That's forget about it. So essentially the technology is there. We just need to understand how to operate with it, right? I don't think it would be fair to say that humanity never had anything disruptive. We had industrial revolution before, right? And people were worried about the machines. I also like those pictures from 80s where there's all these high school teachers demonstrating in front of the White House with calculators, and they're arguing that they shouldn't allow calculators in high schools because kids would stop know how to learn and count, and they're not going to be as intelligent as they used to be. That's a reality. That it was like a perception that that's a danger. And right now we smile at it, but we just adopt it like that. And we know how to use it. Like when they teach kids right now, the calculators use at the proper time, at the proper age, right? But we don't try to outcompete the calculators. So I think that would be the situation for a long time with AI as well. I don't think personally that we are that close to superintelligence yet, right? Yes, it's exciting technology to play with, but there's a lot of missing gaps. It's hard to say how long it is until we get any form of real intelligence from it. But it's already very capable. I'm saying that that's going to be a gradual process. I don't feel like we're going to wake up one morning, it's going to be a Terminator scenario and everything is captured and we out of a sudden that's intelligence get outside of the control. You have to build this intelligence first. It's like we are in the early innings, in my opinion, of building it.
It's interesting how our perceptions change over time, because it was a similar thing with chess. I think in the late 1970s, it was thought that if we could build a chess computer that could beat, the best human, then that thing would be generally intelligent. And of course, with experience, we've just changed the way we think about things. But just final point on this, like the physics thing, because you can think of deep learning as being a form of physics in the sense, what is physics? It's modeling the world that we live in. But Noam Chomsky said that he thought that these language models are not a theory of linguistics, because they don't, a theory should explain. It should carve the world up by the joints and actually tell you something about what it's not as well as what it is. So what do you think about this as a form of science? Do you think it's legitimate?
I think it's legitimate. And in general, I like when the words like that are given to interdisciplinary stuff in general, that's in the intersection of multiple different things, like say physics, biology, computer science, and these particular examples, because I think those are where the biggest breakthrough happens, not in one narrow field, but actually across different areas. It requires much bigger vision. I'm really excited about the whole field that's got a recognition. Award is an award. There is definitely, credit comes with this. But what I think there's definitely an effect that we're all excited about this technology right now, and people want to recognize it because it's so transformative, right? And again, people inventing a pure elements of, say, biology and physics deserved it as much as the people that inventing the methodologies or measuring tools or even modeling simulation tools. They are like as important. Like, for example, when we think about the brain, it's important to study the brain from the physical perspective, but there's only that much we can do. But so is modeling, because the modeling allows us to do things we never can do in the physical world. So it's important, especially if it's proven to be so disruptive, right? It's not become just like a tiny experiment. It actually changed the world in a way that is hard to imagine before. Like, you ask someone 10 years ago how disruptive AI would be in our life, it would be very hard to imagine, right?
Do you think that, let's say NVIDIA, for example, do you think that their stock price is going to continue to go up? Do you think that our compute demands and GPU demands are just going to continue to explode, or do you think it will level off?
Wow, great question. So, well, the short, honest answer, like, for example, I have some stock myself, and I I still do own NVIDIA stock, so I still believe that they will grow. I think that's the most honest answer. Like, I can come up with any explanation, but that's the reality what I'm doing myself. How far it can go is a hard question, right? Like, but I do think they deserve to be where they are right now because they believe in this technology early enough. So they got lucky in a way that like the chips they had at the time ended up being a good fit, but a lot of people lose those opportunities and they didn't. They understand and capitalize and do a huge investment into software ecosystem beyond just building chip, which is a great vision by the company and their founders on like what's really needed. And I think they're getting benefits of that. How far they can go, it depends on like a lot of that things in where the stock is, it depends on people's expectations. Sometimes they show phenomenal numbers and people's like, oh my God, they didn't grow by another 10x, so they're like not doing well. And it's like ridiculous. Like their revenue and everything was growing by huge numbers and the stock next day can go down. I look at that as like, that's ridiculous. But there is like a lot of that gambling that goes into stock shares. But I think as a company, they had a chance to become like continue being a transformative company in the space. But I also think they're not going to be the only hardware providers moving forward. There will be other people with the hardware as we see right now. And because of that, the world can utilize all of them. But I would expect for the next, say, safely to say, I would say 3 years, right? I can't see that anyone would bypass NVIDIA at the top, right? I think they're going to be a dominant player in the space for the years to come. And definitely for the next few years, I don't see anyone who's going to be easily top them. Like, I don't see this coming. I don't know what that means for the shares and the expectation in the stock, but I think they're going to be one of the top companies for some time now, for a good reason.
Awesome. Gennady, I've thoroughly enjoyed this conversation. Thank you so much.
Me
Folks
too.
at home,
Thank you.
if you want to work for Gennady, please reach out to CentML. I'm sure you're hiring good people, right?
Always growing, always hiring. So please reach out.
Thank you so much. It's been a pleasure.
Yeah, it's been a pleasure for me as well. Thank you.